So hello everyone, and can you hear me loud, and is the correct screen is sharing for you?
Yep, sounds great.
Fantastic.
Yes,
Okay.
perfect.
Thank you. So I'm seeing my friends here, Ali, Arash, Fatima, Milad, Vahid. So cool, Asma. Very cool. So I'm so glad to be here. Thanks for Helen, Rob, and all ACS Cytometry Conference Society that give me this opportunity to be here with you guys for a fascinating conference today and a workshop about microfluidics. So today we are going to understand what's microfluidics and how microfluidics would help in flow cytometry and in cytometry society. So to start with my presentation, I would like to tell who I am to those that do not know me. So I'm the last month actually PhD student at University of Technology Sydney. My supervisor is Professor Majid Ibrahimi Varkiani. So together we have found two companies. So I'm co-founder of Microgenesis, is a company that we are reframing the way that we are treating the infertility. And I'm inside another startup company spun out of the university for the bioprocessing for the large scale cell processing. My area of expertise is about microfluidics, why for accurate positioning of cells and particles. And just 2-3 days ago, we won the HDR Excellence Award 2021. I was the best researcher of New South Wales at 2020, and we got the most innovative prototype and People's Choice Award in UTS Accelerator 2019. Today I'm going to tell you how this session is going to be organized. Our workshop has two parts actually. The first part is about, a more introductory part. So I would like to say what is cytometry, what is microfluidics, and we'll talk a little bit about the market size of microfluidics. We will talk about different types of microfluidic platforms. After that, I will give you a quick break. We will have question and answer session. Then after that, since I know some of my friends from Iran that are really expert in numerical simulation, I want to talk about how we should have an efficient numerical simulations, because my very background is actually mechanical engineering, and I'm a little bit expert in these sort of softwares like console, like ACS, and I know how to model fluids and particles within a channel. So we will talk definitely about numerical simulations. I think this would be for the first time that we are doing this. After that, we will talk about microfluidic device fabrication. We will talk how we can fabricate microfluidic devices. We will talk about the power of 3D printing. And at the end, I will talk about examples of how microfluidics and cytometry is going to be applied for life science researchers. So since we are going to have some interaction with you guys, I would appreciate if you open a Slido in your phone or PC. You can just easily go to slido.com, and then you can join this session by this number, which is down in here. I will show you during the question as well, but if you will do it and prepare it now, I really appreciate it. Okay. Let's begin the workshop now. So the first question is that we are in ACS, we are in Australian Society of Cytometry. So the question is that what is cytometry? So cyt in here means cell, and metry means measurement. So cytometry means everything that is related to measurement of a cell. For example, imagine you have a cell population and you want to know how much of those cells are alive and how much of those cells are dead. So what are you doing? You are doing cell cytometry. You are measuring the cells with the criteria of live and dead. So who is cytometric? Who is the cytometric guy? is a guy who is expert to do this cytometry. And what is flow cytometry? Flow cytometry means the cytometry that is happening within a solution. So you have a solution of particles and cells, and you want to do the measurement of those cells within the device that you have. So the question is that what are the components of flow cytometer? So a flow cytometer, as you are seeing here, let me make it to pointer option here. So we will have a laser where particles are passing and interrupting the laser. We will have a fluidic system. So when I'm calling fluidic system, all of you should understand that microfluidics will gonna play a role exactly in here. And we'll have an optic system where we want to recognize and identify different wavelengths that we have in here, different lasers that we have in here, and we have some electronics to convert the optics system, the optics quality data that we get through our system, and to analyze them toward a specialized software that we can see them. So if you are seeing the components of a flow cytometry device, you are understanding that for using a flow cytometry, you have to have a specialized software and you have to have a PC. So here I can tell you that having a portable or a handheld flow cytometry device, or let's say cell cytometry measurement device, would be something really beneficiary in this area. So here is how the flow cytometry is working. I have a main fluid where particles and cells are passing through this stream. I have sheath flow where the sheath flow pushing the cells and particles toward the center. So you are seeing now my particles are at the center. They are entrained through the channel. And then when they are passing through this path, they are interrupting this light that you are seeing here. The interruption of this light will give us two different wavelengths, two different, let's say, side scattering and forward scattering. The forward scattering, as you are seeing here, and as you are seeing in this video in here, will show us how is the size of the cells. So we are measuring these cells, and the throughput of the system is extremely high. And based on the passing the cell, we will understand what would be the population or what would be the size of the cells through the device that we have. For the side scattering, where we are getting from this channel, we are getting to understand what would be the granularity of the cells. And we will understand the complexity of the cells that we have through the system. So these are the components of a flow cytometry device that we are using. So the question here is that how particles are moving through these systems. So I told you we have a sample flow where particles and cells are flowing and passing through these. And we have a sheath flow where it focuses, where it narrows down the stream to make sure that our particles are in a single line. If my sample has relatively low pressure, low sample pressure, or let's say low flow rate, okay, the stream that I will have would be a narrow stream. So my particles then are forced to be in a single line. Means I entrain the particles. That is something really good for data analysis of flow cytometry. However, if I increase the sample pressure, if I increase the flow rate, so when I increase the flow rate, the power of my sample would be increased. So the width of the laser beam for me would be increased, means that the chance of having a single streamline through the flow cytometry device would be less here. So it really depends how you want to analyze your flow cytometry measurements. You want to do with low sample pressure or with low flow rate, so you have to spend more time. At the same time, you will get high accuracy. If you want to increase the sample pressure, if you want to increase the flow rate, you will do the analysis much faster. However, the sample accuracy will be compromised. I just bring this slide to tell you that cell entrainment is important. So I want to say that instead of having this complex system, If we use one of those inertial microfluidic devices, if we use one of those microfluidic devices that has single inlet, not two inlet, and they can train the cells from a center line, then we really don't need this complicated setup for running the particles through a flow cytometry devices. So something that I have to add in here is that flow cytometry is not only for measurement of the cells, they can be used for separation of the cells as well. So when the cells are passing through here, through this system or through this system, they are forming a droplet. Then these droplets are getting deflected by the detectors that we have based on the fluorescent detections that they have on their surface. So we previously tagged them, and then we assign each outlet or each fluorescent particle goes to which of these outlets that we have assigned in the system. For example, we can say, I don't know, the particles that have positive charge go to this one, the particles that have negative charge go to this one, and the particles that are waste, we don't give them any charge and they can go through the system in here. So you are seeing here that my flow cytometry device is able to do the particle separation very easily. But I have to remind you that microfluidics had the opportunity of separating the particles, let's say, much easier than the complex system that you are seeing right now. So what are the commercial flow cytometry devices? The left is among the first generation of laser flow cytometry devices. That was in 1984. The right one is one of the most advanced BD-S6 cell sorters or flow cytometry devices that exist in the world. We are lucky that we have this in our UTS. And I'm using this machine. It's really advanced. We have lots of channels, we have lots of lasers, and it's a really advanced system. You are seeing we have sheet flow, we have wash flow, we have a dedicated system. So the system is really great, but it's bulky. You are seeing that it's occupied half of the room in our system. At the same time, really at the same time, 1 year, 2 years ago, some talented scientists have developed a commercially flow cytometry device that the heart of the channel is a simple microfluidics. So you are seeing these guys, the Wolf cell sorter. They are doing the thing that these guys are doing, but in a much smaller footprint. So I have to say that these guys have developed the benchtop flow cytometry devices. And based on the current pandemic that we are all experiencing and we are suffering from the contagions of these viruses, you understand and you appreciate how portable devices are really beneficial to do the experiments. And I think we are going toward to make the things more compact and more benchtop to make the systems more bulky. But definitely this doesn't have all capabilities of the previous slide, the BD cell sorter, but at least it's a nice alternative for this application. So since I'm introducing these commercial flow cytometry devices, that the heart of this microfluidic, this cell sorter actually has a microfluidic system, I would like to talk about that. What is microfluidics? So microfluidics, you are knowing that micro means movement within a channel and fluidics means fluid. So it means that when a fluid is passing through a network of microchannels that has the dimensions between micron to nanomillimeter, then we are talking about microfluidics. So in microfluidics, the physics that we have in macro is not really what we understand. So we have to understand the macro and nano physics to understand how particles are moving through the channel. So let me be a little bit frank with you. For more than 5 years, I think I'm really focusing on the particle movement toward microfluidics. And I can say each day that I'm doing the experiments, these cells, these particles really surprise me because I'm seeing novel phenomena, novel behavior that I still cannot understand what's happening. So just want to say that really microfluidics is a complex phenomenon. At the same time, is an easy concept. and it requires you to perfectly understand what's happening through the system. So what are the benefits of microfluidics? Definitely, they are easy to use. Most of them these days are handheld, or if they are not handheld, they can be run with a simple peristaltic pump or storage pump. They have the ability of portability. They are automated. We can multiplex microfluidic systems, so we can create macro microfluidic systems, what we are doing currently right now in our lab. We have the ability of parallelization. We have much faster reaction time. In an article that we have published in 2020 in Advanced Materials, Applied Materials today, actually, we showcase that through a microfluidic platform, we can reduce the time of a reaction from 6 hours to 110 seconds. So it had really faster reaction time. And the analytical sensitivity and temperature control is much enhanced through the microfluidic systems. So everything for the journey of microfluidics for me in Australia starts from this project that was published in Applied Materials today again as well. What happens here? We have lots of biologists in our lab or in our group that their everyday usage or their everyday experiment is to do particle conjugation. Means that they have to put or dump a batch of particles or a batch of cells and then put antibodies beside them, wait for 6 hours, wait for 10 hours, wait for 20 hours, wait overnight, to make sure that those particles are getting conjugated toward the cells or particles, those antibodies actually, and then do their experiment. This is a preliminary step before doing their experiment. So it means that before they want to do the experiment in our lab, they have to wait at least 6 hours or 24 hours to make sure that their samples are prepared. So we start with this project. We have lots of brainstorming with different experts in this area on how we want to quantify, how we want to say that, okay, our system is better toward the conventional method of particle conjugation. And then, since I have a quite good background of developing micromixer devices, we have developed these micromixer devices that you have to just put the beads at one inlet and put that, for example, chemistry that you want to connect the antibodies through the other outlet. And you are seeing that everything is going to happen through these microfluidic channels super easily, without any problem, without any complications, without any, let's say, waiting or something like that. And if you want to have the multiplex version of this system, you have to just easily connect two of these microchannels together. So it doesn't need really complex system or anything like that. It's just a simple Lego-like microfluidic devices for these applications that we have developed. And you are seeing that how perfectly particles are conjugated to the cells. And here is the same, that we can coat gold nanoparticles through the system that we have developed. So based on this, I wanna tell you a great map, which is the microfluidic market in the whole world. So those areas that are highlighted by red means that the market is dominated by 1 to 5 major competitors or major players in the world. For example, in these areas that we know where are them, or I don't know, in these areas or in this area, 1 or 5 major players in microfluidics market, for example, Illumina, for example, Biorad, they are dominating the market, means they have their product, everything is consolidated there, and people are happy to use them. This is something really great. And this is something, this shows that the microfluidic market is going to establish them. Here, you are seeing that the microfluidic market is booming, means that many different groups are trying to get their attention and to get others' attention to sell their product. And surprisingly, in Australia, we don't have any dominant player, but the system is highly competitive. So this map is really a nice map. That was the source is for motor intelligence, and it shows that the microfluidics is booming. Microfluidics actually is coming. Whether we like it or not, we have to face that the devices, the reactions, I don't know, all sort of laboratory experiments that we are going to do in the very near future are going to have microfluidic components in different areas in those channels. For example, you can use microfluidic devices for bioimaging. So instead of putting your whole cells or petri dish in front of or under upright or a microscopy, you can do easily integrate one of those lights within your channel and then image them live without any problem. So for sure, you can use them for separation science. Our group is actually expert for the separation science. That's very good. We can use them for drug delivery, means that you can have different dosage of drug. And then, for example, imagine that you have to understand what dosage of chemotherapy is better for you. So this is not possible unless you are using microfluidics to perfectly understand what dosage is better for you. So definitely you can use for cell culture. New cell culture microfluidic devices have been emerged and they are using. And we have to do for diagnostics. We have published a paper in 2021 when we have developed a portable, very small portable platform for detection of COVID-19. Means that if you are coming to Australia, hopefully very soon, I'm seeing many of my friends that they are coming. So instead of waiting for your PCR results, all those sort of complications, you can use our machine. In less than 20 minutes, we will tell you whether you have a COVID-19 or not. So this is something really cool and really, really fantastic. This is just one example that how microfluidics in environmental application can be used. For you know that in environmental application, you have lots of creatures that you have to analyze. Imagine you want to modify the cells. How you want to modify those cells or those bacteria or those organisms. So we have developed, and there are some commercially available electroporation systems that you can easily do the gene transfer. So you don't need to do those chemically adaptive gene transfer anymore, because we know that they are working, but we have better system to make the throughput, make the efficiency much higher. At the same time, less damage to the cells. So you can understand what are the ions into your system, what you can separate actually. You can separate the different components to make sure to understand that you are understanding what are the different components. You can have some sensors for water contaminants measurement that those sensors can be portable. These are all sort of applications that microfluidics only in environmental science can apply. So imagine microfluidics in mechanics, how big is that? Or microfluidics in life science research. This is really booming, really booming, really booming. So since cell separation and cell mixing, let's say, these two are two really important components of all laboratory experiments. At the first, I would like to talk about what are the conventional cell separation techniques. So we have density gradient centrifugation. So for density gradient centrifugation, you always use a density gradient medium. So you have different cells, and then after doing the centrifugation, the density of that medium is between the density of the components that you want. And then you can easily select those guys that you want. But the question is here, all these methods, especially the density gradient, they are related on the technician. For example, I might have shaking hand. So if I have the shaking hand, I cannot perfectly collect these guys. You know what I mean? So for doing the lab technique, for doing the conventional cell separation techniques, you really need to have expert user. For example, for the centrifugation, this is before centrifugation, this is after centrifugation. But you really cannot separate different components of a cell through the system. You can have a plate of the cell which is mainly used for cell washing. You can do multiple centrifugation system techniques. That's true, but it still needs lots of hands-on experiment for you. There are two really developed systems that are available commercially, and they are in all laboratories. One is FACS, I told you, which is for selection of a specific cells based on the tags that are in their surface, and we have MAX, where we use the magnetic property for separation of the cell of the target. So we can label our cell of interest to get them from the sample, or we can label other components to get our samples free without any labeling in the system. Still, we have one common technique in, I would say, all laboratories, which I would say this is cell washing. I don't know if there is any biologist in the world that didn't or don't or do not want to do cell washing, which is a really time-consuming process for an experiment. So imagine you have cells, you want to stain the cell, you have to wait for a couple of minutes or a couple of hours, it depends on the stain, and then you want to remove the stains and you want to wash them. So what we are doing here in our lab is that we wash the cells 3 times, 4 times, 5 times with the PBS, and then we are resuspend them in a media. But we all knowing that the centrifugation will going to damage the cell. We are at the same time imposing extra pressure, extra gradient to the cells as well. So which means that really having a simple microfluidic devices for cell washing is something that's really easy. Or imagine when you finish the work that you have with the cells, you want to freeze them. And after you freeze them, you want to, for example, after 2 months, you want to use them. So the research shows that when you unfreeze the cells, you will have more than 50% of your cells die. So you have a mixed population of live cells and dead cells. So how do you want to separate live cells from dead cells? These are some really challenging phenomena that is happening in our labs, and we believe by developing really portable and easy to use microfluidic devices, we can answer all these questions. So if we want to talk about microfluidic separation, we have 2 different kinds of microfluidic separation. One is active microfluidic devices, where we are using an external force for separating the particles, and then we have passive microfluidic devices, where we are using the geometry features or the hydraulic or the hydrodynamic forces within a channel to separate cells or particles. At the same time, we have some hybrid channels that they have both some components of active and some components of passive microfluidic devices, or they have 2 different components of active or 2 different components of passive microfluidic devices for separating cells and particles. So I really want here that you help me, that we have some interaction with you guys here. So if you join the Slido, this is the website, slido.com, and when you press this number, please let me know which one do you prefer. Imagine you are in a super advanced laboratory and you have the ability to buy every kind of microfluidic devices that you want. Which one do you prefer? Do you want to have active microfluidic device? Do you want to have passive microfluidic device? Or do you want to have hybrid microfluidic device? So let's see how's the interaction here. Okay, we see that hybrids are getting dominated. Cool. So yes, Thanks. Amazing. Really, I don't expect to see this. To be honest, I really don't expect to see this, but that's cool. If you join Slido and then use this number, you can see this question right now, and then you can answer the question. That's really cool. I really don't expect to see hybrid microfluidic platforms are this much popular actually. My vote would be towards something else. So that's cool. So it shows that around 70% who are really interested in microfluidic devices, they prefer to have hybrid systems. So for the answer for this selection, I would say would be because they are getting the synergic effects of two different or more than two different components to separate cells and particles, which is actually true. The second position goes toward active microfluidic devices, very interesting. So I would say those guys who are voting to active, they are seeing active microfluidic devices for being more efficient toward the applications that they have. For example, we know that acoustofluidics are really high efficient microfluidic devices, both for sorting and for mixing. They are really, they prove themselves actually, let's say. But at the same time, the throughput in their system are a little bit low. So those 9%, they vote for passive microfluidic devices, I believe, because they mainly look for simplicity, because passive devices are a little bit simpler than active or hybrid. But at the same time, they can get higher throughput in their system. So that's very cool, and that's very nice. So now my next question here is that, let's go to the next one. Here, among passive microfluidic devices, which one you have experience of working? I want to know, how is the experience of working toward using passive microfluidic devices? For others, may I ask to write in the chat? Oh, I'm sorry. Oh. So is this poll active right now or not? The passive one. Okay, it's active. Those guys who said others, may I ask to write the name of passive microfluidic devices that they have used in the chat box? Yeah. That's very cool. And I like the vortex. That's really fantastic. That's cool. So for others, I really want to know what are the devices that they have used. So if they can write it in the chat box, I really appreciate it. For inertial, so I know a couple of you guys here, so I know that they are working for inertial, definitely, and they are expert, much better than me. Inertial is a cool system. The throughput is really cool. The separation efficiency is cool. I would say this is one of the best choices that we can have. Vortex is actually very good. We have Vortex Bioscience that is developed by Dino Di Carlo, and then it's running by Sujun Hair Claire in USA. They have some contacted towards some of our members 2-3 months ago, actually. So they are working very good. And we have a commercially available product that's called Vortex Bioscience in the market. I talked to the CEO. They are they have different sorts of components to be developed in the future, and they are keep optimizing the channel geometry, which is really good, and the device efficiency is really good as well. So this is among the passive one, and at the last question would be the active one. So I will move toward the last question now. Okay, among active microfluidic devices, which one you have experience of working? Fantastic, acoustic. Beautiful, electric, acoustic. Cool, cool. So this is very cool. It's showing that acoustic-based separation is really popular, and it is really. The separation resolution I told you is really high in acoustic-based separation, and there are lots of research around acoustic-based separation. I know one group is commercializing an acoustic-based flow cytometer in Singapore. There is one company which name is ACS Sorter. I will show you a little bit later that they are separating cells based on acoustic force, and they have a commercially available product that's very nice. And electric base is the same, but I would say to those guys who wants to work in the active area, really consider magnetic base. I will use it in the future, in a very soon future, actually. Magnetic base are really cool because the setup is so simple for you. You can have a simple magnet to get the things done for yourself. And for the optics, we have the Berkeley Light. I don't know if you hear the company name or not. They are the master in cell sorting. They can manipulate, they can move every individual cells super easily, super nice, and really appreciate the product that they have. That's cool. So we roughly understand what's happening here. We will have more Slido in the future. For now, let's go and talk a little bit about deterministic lateral displacement. We don't have any usage of that in our group, but I would say that this is a very nice concept for separation of cells and particles. So the concept of separating is having the pillars, and then the cells and particles are moving toward different streamlines. Those are that is smaller goes through one streamline, and those are that are bigger goes through the other streamline. And this will cause to have a separation based on the lateral displacement of the particles. So this is one of the great examples of DLD devices that was happened by the great Mehmet Toner group in MIT. or Harvard, I'm not sure, one of these two. So at the very beginning, they have the blood cells and they have the running or sheath buffer. The blood cells goes here and RBCs, platelet, and other blood components are getting separated through these outlets. And the big components, which are white blood cells and CTCs, are coming through the sheath buffer. So in the sheath buffer that you are seeing here, we don't have anything like RBCs, platelets, or other components. So, this is actually an example of hybrid microfluidic devices. Then after hydrodynamic sorting, we will have inertial microfluidic sorting. So they are passing through these microchannels that were developed in 2007 by Dino Di Carlo, that was published in a PNAS paper. And he was able to sort and entrain particles in a single line. And after that, since WBCs are, here CTCs are labeled with magnetic bit, they put a magnetic source in here. So CTCs are going to get collected from this outlet, and WBCs that they don't have any tag on their surface will collect from this system. So what they have developed is that they claim that they have a hybrid microfluidic system, that they can separate blood cells, they can separate CTCs out of blood cells without any dilution. So we have some dilution in here for sure, but the blood itself can go straight away. Or the system is really cool for the DLD structure. This is another example of DLD devices that was published in 2020. So for those guys that have access to 3D printers, this is a 3-dimensional DLD, which is really nice, and the concept is really fancy. So instead of having a planar DLD, they have a 3D structured DLD for separation of cells and particles. They fabricate these 3D DLD cartridges via 3D printing method for sure, and they prove that their system is working very efficient, and they were able to publish their work in Chemical Communication from RST journal, which shows that the concept is a concept that people like. And since it's in 3-dimensional, I would say that it was a really new and nice concept for further improvement of DLD devices. However, we all know that DLD devices are suffer from a different, special problem, which is throughput. So throughput in DLD microfluidic devices is really, really, really low. And the system has prone to have some clogging issue, having some bubbles in the channel, and all those sorts of problems. What in 2020, the Austin group, if I'm not wrong, has proposed. So this group is the pioneers of DLDs, the guys that published the first DLD paper in 2004, I think, in high quality journals like PNAS or Science for separation of cells with really high accuracy. So they have proposed that instead of using those sort of pillars for separation of particles, if you have some indents like this, and if you have fresh buffer and the samples, you can separate fresh buffer and samples from each other very easily. So you are seeing that, for example, in here, large particles are going straight and small particles are going through this outlet. And you are seeing how nice is the separation quality. And at the same time, the throughput is so high. The throughput is really high. So I would say that this is one step toward the commercialization of DLD devices for the real, to be a real product. Because if you want to have a real product that is based on DLD system, you should address the challenge of clogging, address the challenge of bubbles, and I would say these articles can address that very nice. The second concept that we have is pinch flow fractionation. So what is pinch flow fractionation? So the concept is that all cells or particles are coming from this side. They get pushed toward the wall by a side flow, by a buffer flow. And since different particles have different volume, different diameter, they get focused to different streamlines. and they get separated from different outlets. The concept is relatively simple. Mr. Yamada is the one who developed these microfluidic devices around 2004, I think, but lots of new applications are coming these days. For example, here is the system of pinch flow fractionation, but they use the density gradient of the particles as well. Means that they have sort particles based on their size and based on their weight. So you can separate the particles based on the two criteria rather than one criteria, which is very nice. The other concept is this one. So if you have a simple obstacle, then particles sense the obstacle. We call them these snake-like particles, snake-like obstacles. And then since those guys will sense the obstacle, they can focus more toward the obstacle or more toward the extra one, and you have a more distance toward two different kinds of the cells for the separation. So I know the concept is really simple, but just want to say that through a simple concept, this nice group can publish this really nice article in Lab on a Chip in 2021. Means this article around 1 month ago gets published in Lab on a Chip. Lab on a Chip, I don't know if you know or not, is one of the best journals that we are trying to publish our works there. And they are using the really nice concept for separation of sperms from the bacteria or from the virus through this concept that I told you. So they have the sperm cells and the bacteria from one outlet, the inlet buffer or the sheath fellow comes from the other one, they pinch them toward the wall. So the sperm one comes through this outlet and the bacteria goes from this outlet. That's it. As easy as I'm talking about, as easy as you are seeing what the paper is published in Lab on a Chip. So it means that sometimes having a nice idea will lead to development of nice and great articles down the road. So don't forget this fact that you shouldn't always create really fancy microfluidic devices to do something strange. No, you can use some established methods, but further improve them, improve in terms of the concept or improve in terms of the application to make sure that you have a nice publication out there. The other nice hybrid platform system that I really like the article is the pinch flow fractionation by both viscoelastic forces or by inertial forces. So they essentially say that after we pinch the particle, we give them enough length to make sure that they are focusing based on elastic or based on inertial lift forces. And then based on this, they will claim that they can separate two different particles based on the morphology in these channels, which is really great. So they can separate spheres particles from peanut particles and can publish these articles in Analytical Chemistry in 2015. So the other concept that is a nice concept and has been used a lot is hydrophoresis. This hydrophoresis has a long history of development. And one company, I think the name is FE Bio or Cell FE or something like that. They are using the same concept, but another definition for doing the intracellular delivery. They have a nice patent out there and they have used the same concept. They are using the groove channel. So if you follow Alex Sieve works from 2008, 10, 11, they have developed lots of numerical data, numerical validation toward the functionality of these channels. They can separate size based on their stiffness. They can separate the cells based on their size. They can separate based on their morphology. And now they are applying that concept toward intracellular delivery, which is something really hot in these days. So the concept of hydrophoresis, for example, here is displayed. Easily, they have put one diluted whole broth in here, and then they have droplet collections. You are seeing that the droplet collection in the vase has lots of RBC and WBC, so the droplet is getting red. But here, our droplet is transparent, which means that we have the platelets here. And the bottom one is showing how they can scale up their system. So you know that one of the main problem of these methods is that they are low throughput. All methods that I have shown you so far, they are low throughput. So one way to improve the throughput is that you scale up the system, you multiplex them, you parallel them to improve the throughput. For example, if here we have 10 channels, the failure rate would be 10 times more than the previous channel. It has lots of issues, but at the end, it will work. And you are seeing that how they do the waste droplet and how they do the droplet collection through the system. And the last one toward microfluidic devices for cell separation is inertial microfluidics. So this field emerged around 2007, 2008. It's not emerged, it was there. The field was there from 1956 when they report these applications, but really the guy who focused on these applications and showed them in terms of the microfluidic channels was in 2007, 2008, and hundreds of articles so far has been published through this concept. The concept is how you can use a simple channel with really high throughput for separation of the cells based on their size, based on their morphology, based on their shape toward different outlets. This is how they are saying. For example, here, it shows that when a particle is flowing inside a channel, it is under effect of two forces. One is shear gradient, so that's really obvious because this is because the fluid velocity is parabolic, so it will feel some sort of shear forces on top of the surface. And the other one is wall effect. So wall effect in microfluidic devices is something new. It's something really new, because in microfluidic devices, the particles are bounded toward two walls. That's why we don't see this phenomenon in a river, but we are seeing this phenomenon in a channel. Because in a river, they don't feel the wall, but in a channel, they are feeling the wall. And this wall is causing all inertial forces in the microfluidic devices. The channel that you are seeing right now is a straight channel. We have a spiral microfluidic channels as well, where the throughput is again much higher than even a straight microfluidic channel, and based on the forces that you are seeing, the particles is getting focused toward different position. Here, the small one goes toward the outer wall, the large one goes toward the inner wall, and then we can separate them toward different outlets. And here is what you are seeing. For example, white blood cells are getting trapped toward this space, these DIN vortices, but CTCs, which are larger in size, they are under another effect and they get focused toward this one. So if you have one outlet in here and if you have another outlet in here, you can separate cells with different size or different morphology or different even deformability in your microfluidic channel, which is based on spiral microfluidics. So the focus of our group is really on inertial microfluidics these days, where we are leveraging this phenomena toward different applications that we have in our mind. So since we are in ACS cytometry conference, that's good that I show this example of devices. So you are seeing that the Hamway group in 2019, they have developed a very nice impedance-based inertial microfluidic devices for the measurement of the cells. You are seeing that here is where the WBCs are going, here is lymphocyte, here is, different sort of outlets are assigned for different applications in this channel. And then at the end, you are seeing that based on the impedance profile that they have, based on the stage size and the opacity, they can measure different sort of cells that is getting collected toward the outlet. And this is how the channel is working. First, it goes through a DIN fellow fractionation, means based on DIN fellow vortices, they are separating the particles. Then they are doing flow rate reduction to make sure that they can govern the exact flow rate that they want. And then based on the impedance detection, they can detect what they want. And this is a cool application of inertial microfluidics towards something that is going to get a commercial application in their future. And they show the proof of concept of this device for the diluted blood and for the PBMCs, and the device works perfectly. We have also published a review paper in Lab on a Chip 2020, where we claim that, or where we summarize that different microfluidic channels can be used for inertial, which are straight, contraction, expansion, serpentine, spiral, and hybrid. So that's true. We have hybrid microfluidic inertial devices for the separation of cells and particles. So everything begins from the straight channels, but they go to contraction and expansion. They follow up with the serpentine. 2010, 13, 15, spiral microfluidic channels were booming. Lots of publication comes out of the spirals. And then recently, we are seeing hybrid microfluidic platforms for the use of inertial microfluidics. So inertial microfluidics can be used in really many applications. Let's say particle separation can be used in many applications. For example, this is with a company, Cooper, that they have developed beer. They were interested to do the quality control. So they want to see that if the beers that they are producing, how the quality is, and if they don't have good beers, you know that it's some sort of brand reputation. So they are using all those sort of multitude of experiments or doing the PCR toward the system and those devices that they have. The thing that we have proposed to them is that you can use our specialized inertial spiral microfluidic devices. Then you can separate those cells that is in your mind from the channels, from the solution that you have, and then you have to just analyze that particular or that specific solution instead of doing the whole batch, which saves a lot of time from them. And just because of the concept that we have developed, this get a hot collection article in 2019. And you are seeing here, we have two different outlets. This is the microscopy images. Here we have these sort of output from the one outlet, and here we have the other one, which means that the concept of inertial microfluidics works perfectly for this application. The other application that we have published in 2021 very recently in scientific report, this is toward the company that we have, Microgenesis, is a microfluidic approach to rapid sperm recovery from heterogeneous cell suspension. So actually, the problem of the microtesting, those guys that doesn't have motile sperm, so they have to get a piece, and then that tissue has a mixed cell population. We claim that we can use that mixed cell population, and then based on the fractionation that we have, we said that we can give you a relatively pure fraction of sperm cells. So imagine imagine a biologist wants to analyze these mixed samples. That would be something really hard. The outlet that we are getting to that guy is just this, means that sperm cells with a few around 20-25% of our red blood cells, because red blood cell size with sperm cells, they have some overlap. So we have to further improve to remove the sperm cells. But at the same time, the amount of our red blood cells here are not too problematic, and we can analyze them really easily. And you are seeing here that in the waste outlet, we have just cells and epithelial cells and particles and things are here. But in the target outlet, we have the pure sperm cells with a little bit red blood cells as well. This article gets lots of attention. We have lots of, we receive lots of emails to sending the channels for different clinics because they really like the concept and want to apply in their lab to make sure that they can use it toward the patients that they have this, because this is a really problematic problem for those who are working in the sperm area. But to further understand how these microfluidic channels, how these spiral microfluidic channels are working, our group has developed some cool studies, some cool fundamental studies on the size, on the width, on the height of these microfluidic channels. So we have analyzed the particle movement from the bottom side, and we have analyzed them from the side to make sure that we can see different focusing position of the particles there. This is all sort of numerical data. I know Majid shows this a lot to you guys, but I just want to emphasize that each of these lines here is a single experiment. So it means that this is, I don't know how many experiments they have done to extract this map, but this is something cool toward better understanding of particle positioning toward microfluidic devices that we have our group published in 2019. But we have further improved the concept. We said that, okay, inertial microfluidic does not stop there. We, for the first time, developed a novel method for the fabrication of microfluidic devices, especially spiral microfluidic devices. That is the core research of us. And we have developed a novel fabrication method, and we see different phenomena, let's say new phenomena that we don't even aware of that. And based on that, we have filed 2 IPs to make sure that we can have a cool product out of the findings that we have. So essentially, we come up with the ideas that why all microfluidic channels have to be fabricated via PDMS, via a flexible material. So we developed a novel 3D printed material, and since the material is rigid, we see different phenomena. We see other sort of results that we don't really expect. Based on that, if you want to see here, as the spiral microfluidic devices, the first one actually comes in 2009, where the channel cross-section was rectangular. Then Majid, my supervisor, and Yuan, his friend, in 2012 developed trapezoidal microfluidic spiral channel, but that's stopped. Until recently, very recently, that we showcased that with the method that we have developed, we can have true triangular cross-section based on the 3D printing method. And if you are seeing here, you are seeing that particles are following a single stream band. So if you remember from the very beginning, I told you that it's really important to have a single band toward having particle entrainment. And this application and this channel shows and proves that we are at the good stage for development of a cell trainer for particle focusing for a cytometry application. And these inertial microfluidic devices actually can have the potential of scale up. You can scale up these devices. The scale up can be in X and Y direction, like this that you are seeing. The scale up can be in a vertical direction that you are seeing here, or that you are seeing in this 3D printed microfluidic channel, or the scale up can be radial. So you have different sort of scale up inertial microfluidic devices that can be applied to your system, which is really cool and shows that this system and these methods are really getting mature and mature and mature toward having a commercially validated product. So let me a little bit expedite the process. We have magnetophoresis. When the magnet is on, you are seeing that the particles are getting collected toward this outlet. But when the magnet is off, all magnets are getting collected toward this outlet. So this magnetophoresis, we have a very cool publication in July 2020 by Mehmet Toner group, where they showed that at the first stage, they can separate only CTCs and white blood cells. Then they tag the white blood cells, and then they get the pure CTCs here. So this is the workflow how they do. At the end, they reach to having a pure sample of CTCs and label white blood cells. Those labeled white blood cells are tagged with magnet, and then they separate them by magnet in here, and then they get the rest in here. The total workflow of the device is 40 minutes, which if you compare to other microfluidic devices, you will appreciate and you will say that this is really something cool, and the speed is really high. So the last active microfluidic platform that I want to show you is the acoustophoresis, which is based on the acoustic force. You can separate cells with different sizes toward different outlets, which is really cool. So we have the ACS company that they showed that they can do two different applications for their microfluidic device. The first application is that they can wash the cells and they can wash the samples. So at the left inlet, they will put the sample. At the center inlet, they put the washing buffer. You are seeing when the acoustic field is applying, all the particles are going toward the fresh buffer. So they said that we are washing the buffer. But that's very cool. So imagine instead of doing lots of centrifugations and things like that, you have a simple device, a portable device, a benchtop device. You put two of your samples there, and then you can separate and sort or wash yourself. This is actually what we are going to do, and this is actually the trend of microfluidics is going to do. This next one is for cell separation, actually. So they are applying the acoustic field, and they can separate two different cells based on their size. So this is a commercially product. The name is AccuSort. If you are interested, you can go and see their website. And if I want to compare microfluidic platforms, so those guys who are toward the hybrid platforms, so the separation resolution that you will get here is really high. The scale-up potential is not that much high. The cost benefits, because if you are using a hybrid system to have an active system, then your cost would be high and the throughput relatively would be small. We have different concepts like hydrocyclone or labanidase or illustration, but this is really beyond the scope of this workshop, and I don't want to go toward that. But this is a cool table for comparing different applications. This is going to be published very soon and is online available for you guys. So in this article, we have compared different microfluidic platforms for cell separation, actually the membraneless cell separation, to make sure that we can understand what's happening to microfluidic separation platforms. So that's it. This is the first part of our talk. Actually, the next part I want to, based on the concept that we have developed, I want to have some cool practice here. So if you have any question, if you have any concerns, please let me know. You are free to open your video, you are free to talk, you are free to chat, write your notes, and then if you have any question, let me know. Otherwise, let's wait for 5 minutes to have a quick rest and then continue our workshop. If you have any question, I'm happy to help you.
Thank you for the talk, Sajad. I do actually have a question about the hydrocyclone. I do a lot of work in with platelets, and sometimes we need to wash the platelets before we do downstream experiments. But washing platelets themselves is tends to activate the platelets. I guess my question is, do you have any experience using the hydrocyclone to separate platelets from other blood cells? And furthermore from that, do you know what the shear forces are like in the system and how that might relate to platelet activation?
So I would say this is a really fantastic question. I'm glad you mentioned this, because hydrocyclone is the scope of our research, to be honest. Because the more we are going toward a commercial product, the more we understand that throughput is important. As you are saying that, yes, washing those platelets, because the number of those platelets is too much, and you have to understand that for washing them, you have to spend a lot of time. At the same time, the problem that you have with the platelet is that the platelet size is really small. So what we are developing in our group right now, let me tell you. So we have, based on the 3D printing method that we have developed, we are pushing the boundaries, pushing the limitation of hydrocyclones to make sure that we can fabricate the smallest possible hydrocyclone. So if you decrease the size of hydrocyclone, you increase the separation resolution for less than 5 micron particles, which is what you are looking for right now. In terms of the shear forces, we have tested with other cell types like algae cells or like CTCs or like white blood cells, but we didn't see any activation. So I would say hydrocyclone would be a really good approach for you to continue, but at the same time, you will have lots of problems in terms of first fabrication, then running the sample. Because imagine you have to run the sample with the flow rate of 120 milliliter per minute. So you have to have that much sample to understand what's happening. And that 120 ml will pass through the channel in really 1 minute. You know what I mean? So this is something challenging. And if you have bulk amount of fluid and sample, that would be something cool for you. Otherwise, I would say if you are working with some cell washer that are recently developing in inertial microfluidic platforms, I will show you later, that would be another option that you can do. But I said the main cause, the main problem that you will have is high number of cells that you have at the same time, the dimensions of those cells. These things will make you a little bit at the boundary of having low throughput, high quality, or having high throughput, low quality separation.
Fantastic. Thank you for your answer to that. Yeah, I'm interested to hear that hearing that it can do the separation of high volumes of blood, even if it does need a little bit more optimization in that regard. But for our experiments, we actually work with the platelets themselves. We want to be able to collect the platelets. And quite often we're doing that from fairly small volumes of blood, like a couple of mils. So having a system that could handle the throughput of a few mils of blood and give us a good collection of or good isolation of platelets that have very little ex vivo activation, which is something that we struggle with. That would be a fantastic boon for us in our field.
So one question, are you diluting the blood or not?
So typically to get isolated platelets, you're not diluting the blood, or some protocols will call for a dilution with like a citrate wash buffer first, but quite often what you're doing, we have to hit them with a bunch of platelet inhibitors. Then you're spinning the whole blood at a low speed to get a platelet-rich plasma. And then you take that plasma, dilute that out with more citrate wash buffer, more inhibitors, and then wash it through. But you do still get quite a bit of activation because it's going through the centrifugation steps, and platelets don't like to be handled.
So you are using, I think, PRP application. You are developing for PRP application. Am I correct?
Yes.
Fantastic. So this is a very cool concept, because some of my friends are actually called me 2-3 months ago about exactly the problem that you have, and I want to recommend the same solution. They, I think, can solve their problem. So you might interested because the volume of blood that you have is not too much. If you be a little bit expert in developing DLD microfluidic channels, you might be able to separate all other components and push them, all of them, toward one side, and then get what you want to have from the other side. Consider this in your mind, because you have the lowest amount of activation of the platelet as well. This would be a nice concept for you, I think, because you don't need to have a dilution. Or if you want to have a dilution, you have to be a little bit smart to put the buffer in the side that you want to have those unwanted cells. You know what I mean? Then you don't have any dilution and your system will work perfectly. So consider this fact as well. Having a low dimension, or let's say miniaturized hydrocyclone, would be another option for you. I would say you have to further scale it down a lot So please be a little bit careful because you might have some problems for the fabrication. So talk to some experts in the fabrication of 3D printing materials to make sure that you can make it done. There are some companies that are doing the outsourcing of the part that you want. But at the same time, these are, I think, the viable option that you can do. Inertial is there, but inertial for that undiluted blood is not a really viable option so far.
Fantastic. Thank you for those answers. And thank you for everybody else for indulging my questions. And I will let you get back on with the rest of the workshop.
Okay, so if there's any other question, please let me know.
Hi, Sajad. Thank you for your contribution today. I had a question, and I mean, it was the first time I came across the three-dimensional DLD device.
Yes.
What kind of increase in throughput does going from a planar 2D to a 3D format provide?
So, you know, in a planar format, you are forced to have a low height. That's the height will reduce the, let's say, the throughput that you have. So consider that you are stacking 10 DLE devices on top of each other. So you are improving the throughput 10 times, you know. So now imagine that instead of stacking, you are revolving it toward one side. So still you are improving the flow rate, but getting the same resolution. The only concern that you should have toward fabrication of those channels is that you should be really expert in the 3D printing and the fabrication method. And you should have access to the facilities to make sure that you can fabricate the device. This is my only concern, but the rest, having the DLD microfluidic devices that has three-dimensional structure is really good. And I would really recommend to those guys who are developing numerical methods to work on this area much more, because three-dimensional will give you different forces, and different forces will give you different applications. This is something really cool, and I would really recommend to further continuing.
Super, thank you.
So I think we are not a little bit, more than a little bit behind the time. Let's continue. So I'm seeing lots of my Iranian fellows, Iranian friends that are joining us toward this conference. I want to ask a question now. I want to know, let me go to the question. If the system helps me to go here. So may I know which one describes you better? Are you an experimental expert? Are you a numerical expert, or both? Means you are someone who knows numerical experiment and who's numerical, let's say, simulation, and you know how to work with experiments. Please answer this question. It's really important for me. So to those who don't know how should vote here, you can join, you can easily go to slido.com and then press the number here. You will come toward across the poll here, and then you will understand the question. Cool. So we have around 62% who are expert in doing experimental experiment. We have then those who knows numerical simulation, and then who are applying their knowledge for the experimental. And then we have, okay, now numerical experts are the same as those who are both in experimental and numerical. Okay, so we'll wait 1 more minute and then continue. That's cool. Cool to see lots of experimentalists, you know. So that's really cool. So, you know, my background, my very background is only focused on numerical modeling. So I can't remember how much time I spent on ANSYS, I spent on Adams, I spent on, I don't know, SolidWorks, COMSOL to understand all sorts of these the numerical software. At the same time, I was among those guys who are really interested to understand genetic algorithm, I don't know, ant cloning, all sorts of those optimization algorithms that are exist in the MATLAB. So I spent a quite big amount of time to understand what are the optimization algorithms. So after coming to Australia, after doing some experimental research, what I realized is something that for the numerical guys, first thing is that please make sure you understand the numbers and the dimension. You know, there's something, it's very funny that the first micromixer that I have developed long before in 2016, I think, the dimension was 8 micron, you know? So 8 micron is nothing, but I didn't understand that time that 8 micron is not nothing, you know what I mean? So first make sure that you have a great insight in what is the experimental that you are going to do, or if the thing that you are fabricating, right, you are developing right now, is it possible to fabricate it? This is really important, guys, because I'm collaborating with many of my friends all over the world, and sometimes they send me some channels for fabrication. And because we have one of the most advanced 3D printing facilities in the whole Australia, and I was saying that there isn't any method so that we can fabricate the channel that we have made. So please make sure that you understand the numbers, you understand the dimensions. For example, in a channel with 200 width and 20 height, don't push the fluid with flow rate of 10 ml per minute. There isn't any microfluidic channel system, pump, or anything that can tolerate that amount of pressure. You know what I mean? This is the first hint that I want to tell you. The second one is that, to be honest, numerical simulations are coming to expedite the overall process. They are coming to expedite the process that you are going to do as an experimentalist. They are not coming to complicate the process. You know what I mean? So I'm seeing sometimes, I myself is the same, developing some super advanced code. For example, I remember that I had one micro channel, I linked it with SolidWorks, the SolidWorks was linked to the COMSOL was linked to the MATLAB, then all these three softwares are working together for some simple optimization. And I would say if I will do it in an experimental, I can finish it in 1 day. But my numerical code takes 20 days to complete. You know what I mean? So please make sure that the numerical data, because most of you guys, I know they are really expert in numerical simulation. I know that you are the best in numerical, but make sure you understand that the numerical simulation is to make the things easier, not make the things harder. For example, one thing that I'm seeing these days is inertial modeling, particle focusing modeling toward microfluidic channels. I wrote a review on that. I know everything in this field, and we are developing our specific modules, and might give it to COMSOL, might keep it in our group, but we are in a good position to say that we finally can model the system. But when we model the whole system, I would say the whole numerical simulation will take less than 20 minutes. But the current models that are there, and they do the job, they are more than 2 days, 3 days, 5 days takes for finalizing. The only thing that I want to say to you guys is that first, make sure you understand the numbers, and then numerical simulations are to expedite, not to complicate the thing. Okay, so the question here is that how we want to fabricate a microfluidic device. So we all know that photolithography is the gold standard. There is no other way that no one knows. That's okay, we all understand. But at the same time, for fabrication of the molds, we have other alternatives. The other alternative, which is really emerging these days, is 3D printing. So for 3D printing, you can create the channel directly, or you can create a mold. So one request that I have from you guys, if you want to work on fabrication of microfluidic devices, is that please make sure you understand each of these methods. For example, make sure to understand what is material extrusion, what is vat polymerization, and then based on the need that you have and based on the design that you have, select the proper one. I would say, because we have access to different 3D printers, for most of the time, I don't use the one that has the highest resolution, because I don't need the resolution. I need something else. You know what I mean? So make sure that you understand what is the 3D printing process, and then do the fabrication. What if, imagine you want to create a 3D printed mold? You know, here we said in the process of photolithography, you create the master device. And then based on the master device, you do the soft lithography. So imagine now you want to do the photolithography on top of a 3D printed molds. So 2 different scenarios we have developed in our group. One is that we do a special treatment, a special workflow. The paper is published in Organ on a Chip, actually, 2019. You can see that based on the protocol that we mentioned in here, you can easily create a master mold out of a 3D printed material. The second one is that we change the resin. So we understand that resin formulation is something like this. This inhibits the PDMS polymerization. So we have uncured PDMS on top of the surface. So what we are going to do, we have created a resin formulation, then our peeling off is really easy. So we have a castable 3D printed resin for microfluidic fabrication. So this is our master mold resin. You are seeing the channel is perfect, but here when we are doing with conventional master mold, you are seeing that you cannot see the channel because we have uncured resin on surface of the PDMS. So if you are going to fabricate your 3D printed mold, I would say this might be 2 possible options for you to go. And this is, we prove that the system is working perfectly. We can use the inertial focusing spiral. We can do the cell seeding and things that they are biocompatible. And then we were able to publish this in Advanced Materials Technologies. The other important things that I want to mention here for you guys for doing that, for using 3D printing, is that make sure you understand the limitation of each method. For example, know that what is SLA, what is FDM, and then what is DLP. And understand for your specification part, which of these methods is better. The other one is that consider the printing shrinkage ratio. So some of the printers shrink actually when they are printing. So make sure you consider this guy. Otherwise, the dimensions that you are getting with the dimensions that you want to have would be something totally different. So this is another important part. And make sure to attention to printing orientation, means the orientation, you want to have it flat or you want to have it straight, and then the printing parameters. So one hint to you guys, all those method that I developed through my PhD is just based on printing orientation and printing method. So if you want to repeat them, just if you focus on these two, I would say that you definitely can do much better job than me. So these two are really critical for the applications that we want to do and for the printing of a microfluidic devices. So now, when we understand what's happening toward a microfluidic device, what's happening toward in the process of a microfluidic channel, let's have some case studies example where we can apply these cytometry devices, these cell measurement devices, these microfluidic devices in a real application. So imagine that one of the most important applications that Australia is involved in it a lot is the process of CAR T-cell therapy. So I know all of you guys were in the fascinating talk of Dr. John Roscoe today morning, and you're aware that how complicated is the process of CAR T-cell therapy. I read the news and I understand that for each cycle in Australia, Australian government should spend $500,000 for per patient. So it's a huge burden for a government to do so. So that's why different research groups all around the world are gathering to find some solutions to further expedite the process. And then hopefully we can develop novel microfluidic devices or novel microfluidic based devices for the fabrication of these, for the fabrication of some devices to enhance the workflow of cell-based therapy, specifically CAR T-cell therapy. So, if I want to tell you two commercially available products, one of them is Clinimax Prodigy, which is super cool, super nice. It's a closed loop. So you just put the bag in here, get the output in here in 14 days. That's it. Really, that's it. Everything is automated in the whole system. And the second one is the Cocoon platform that is helping us toward the cell-based therapy. So the Clinimax Prodigy has improved its product. They recently launched an electroporator system for cell-based therapy in the system as well, which significantly enhanced the efficiency of electroporation in the system that they are proposing. But here, so in the workflow that I'm showing to you, what we have in here essentially is that we have to expand the cells on top of the some microcarrier. So what happens here is that in the cell-based therapy or in the CAR T-cell therapy, we get some cells from the patient. We collect the cell of interest. We ship them. Then we select the cells based on any method that we want. We can do it. The method can be immunoaffinity, can be inertial, can be DLD, anything. When we have our cell of interest, then we modify them via some methods, some transfection methods, some intracellular delivery method. Then we have our modified method. For the terms of T cell, we will say we have CAR T cell, CAR T cells here. When we have the CAR T cells, we have to expand the cells. We have to make sure that we have enough number of cells to harvest them and then to put them back toward the patient. So after we have expanded them either on top of a microcarrier or in a culture flask, we harvest them, we formulate them, we package them, and then we cryopreserve them. Then we send them for the administration, and then we inject them, infuse them toward the body of the patient. You are seeing the workflow is really complicated. So one question here. So when we do the expansion in the system, okay, when we do the expansion in the system, what's happening is that the number of cells getting expanded would be so much, okay? When we want to do the packaging, we have to, sometimes we are forced to do this centrifugation in the system. What we have recently proposed for the bioprocessing and for this application both is that we come up with a new microfluidic devices with throughput as high as 35 milliliter per minute, means that each minute you will have 35 milliliter processing sample to concentrate cells toward one outlet and get the rest toward the other outlet. So here we have semi-concentrated and here we have cell-free media. And here is the actual channel in the operation. You are seeing that we turn on the peristaltic pump. That's the system is now working, and we can live monitor that the channel is working perfectly. So this would be a viable solution for industry if they are interested in having a concentrated cell with large amount of volume. The other application here we have developed is an integrated microfluidic systems for separation of cells that are grow on top of a microcarrier to have cell-free, and we have microcarriers free of cells. So you are seeing here, we first have a micromixer, then we have a micro separator, and then we have a micro concentrator. So in a micromixer, we will have enzymes and we will have cells and microcarriers. They are passing through these regions, and then we have detached cells and microcarriers. Means in here, we have A means cells are attaching on top of the microcarrier. In B, we have detached cells and microcarriers. So in C, you are seeing that all microcarriers are focusing toward this outlet, while their cells are focusing toward this outlet. And then we concentrate them at the further step in a concentrator unit. And we have shown that the cells that we are producing with this method are super proliferative. They are working as they are doing with the centrifugation system. We are doing with the same system, but the time that we are spending here is only 4.5 minutes, which is around 5 to 6 hours less than what they are doing in a conventional method. So imagine in that workflow that I show you, if we adopt the protocol that we have developed here toward the CAR T-cell therapy, we will save the time significantly. To let you know that in the ProDG machine, around 10 days is passing for the development of the cells on top of the microcarriers. But we have proved and we have shown that the system that is here, based on all microfluidic platforms, can reduce the time significantly. This is another example where we are using the application of cytometry for the bioprocessing. So bioprocessing is everywhere, even for the development of the vaccines that we are using for the coronavirus, for the exactly current pandemic. We are using bioprocessing. We are using bioreactors. In the videos, in the movies that are all around the world, they are seeing their laboratories. You are seeing the big batch of bioreactors. So essentially what's happening is that some sort of cells have produced antibodies there in a culture media. So what happens is that we want to separate those antibodies from the cells. It means that we want to have a cell-free media. So here is what we are going to do in a small scale, or let's say in a lab-based scale. And here is what we are going to do in a industrial scale. Doesn't matter. The whole thing is that you have to have a big volume of the cells, at least 250 ml, and then you want to have a packed amount of cells coming back to the bioreactor, and then you get the antibodies out of the cell-free media. So this is the solution that we have developed. You are seeing that this is a microfluidic channel that is able, if it is playing, please give me a little bit time. So okay. So it's not playing right now. But it will show that we are showing that our system is able to create a super concentrated cells out of a whole batch of bioreactor. Means that we can concentrate at least 10 times, means 50 ml can reduce to 5 ml. We have further reduced it to 2 ml with a system that is based on a new phenomenon that we have recently found it toward microfluidic devices. And this is showing the flow cytometry data. You are seeing that we have a packed amount of cells in the target outlet, and we barely have cells in here. And if you are seeing here, the separation efficiency in our system is 99.42% after 3 times repetition, actually. So this is really, really, really inspiring and showing that microfluidics is going the correct way toward development of all sorts of processing that is happening in life science research. And here you are seeing how concentrated outlet is look like. So this is more than 50 million cells on top of each other, and I get a photo for you guys to see, have a look and understand that how those simple, the microfluidic channel that do the job for me here is less than a business card. So it's really amazing that a channel less than a business card can do the job of a big centrifugation machine that are selling everywhere, and they are really expensive, do the same job, even better job, because we are not inducing pressure, we are not inducing shear on the cell, and cells are proliferating very well. The other question here is that that right now we all understand that CTC clusters are a really important and vital components in the blood of the cancer patient. So in research in 10 years ago, they ignored these guys, but recently they are of great interest, and we are really keen to know how we can separate CTC clusters and CTCs out of the blood of a patient. So to understand, CTC clusters has different components. They have platelets, they have leukocytes, they have tumor cells, they have everything in their own clusters. So if you are looking for separating these guys through flow cytometry, I would say maybe you can't, because how you want to tag them, with which fluoropore you want to tag, with which cell you want to tag, because anything that you tag, you will get the other population in the bloodstream as well. And for the spiral, we have the problem as well, because the size of these guys is much bigger than the tumor cells, so we cannot separate them through those microfluidic channels as well. These problems and interacting with people that have a real problem of CTC cluster isolation leads us for development of really novel microfluidic device where we can separate cells and clusters from other components. So just look at the center outlet. So we put some cells, we put some particles, we attach the particles to each other to make sure that they are forming the clusters. You are seeing they are passing now. And the channel that we have in here proves that it can separate CTCs from this outlet and CTC clusters from the rest of the blood components, which is really desirable, and which is really, we were looking for this for a long time, and it's around 2 months that we have found this solution for the applications that we are developing with my friend Rob. And we are validating the data right now, actually. The other problem, the other thing that is really critical for us is doing the blood processing and doing the exosome isolation. So recently we have created a rule that we call it highway rule. So imagine you are driving in beautiful streets of Australia. When you don't have anything, you can go in the 3 ways. There is no problem. But if there are some cyclists here, so you prefer to don't go straight, even if the route, even if you have to increase the amount of way that you want to drive to the road. So you are less interested to go towards this outlet or to go toward this highway, let's say. If further cyclists comes here, if you pack here by the cyclist, you really don't prefer to go straight. And this is how we call it highway rule. So just one word to you all guys. Cells sense everything. After 3 years working with cells in the lab, I would say this: cells sense everything. So anything that you apply in the channel will affect the cells and will affect the downstream processing. So this is the main cause that we have recently developed a super novel microfluidic channel for the first time with this throughput 200 microliter per minute for separation of now exosomes. So I would say that the channel that we have right now that is working perfectly for exosome separation has throughput more than 10 times to other even commercially or available in the article for separation of exosomes and has high potential for doing blood processing research. At the same time, we parallelized the whole system and we said that with the throughput of 2 ml per minute, which is around 2,000 times more than all other published articles, with this throughput, we can separate exosome from the central outlet and get everything that we have to be packed and to be pushed toward the side outlet. And since the system is parallelized, you are seeing how perfectly these two are synchronized. So just check the spacing of these two and check the spacing of these two. You are seeing and you're understanding that the system is synced and it can do the job of separation for you easily. So this leads us for connecting different channels for different applications. So imagine you have the whole blood. Depends on what you want to do the post-separation, we can develop the desired application that you want. And this is the way that we are moving. This is the way that we are heading actually. So with my friends that we are developing this channel, especially Rob, that is helping me a lot toward validation of the channels that we are developing. We are creating a company specialized for blood processing, for blood components, for different applications, but all based on simple microfluidic channels, and then by connection of hydraulic resistance and matching the flow rates. So if you want to have a dilution buffer, you can have the dilution buffer here. If you don't have one, you can eliminate it. You can work with the whole blood event. And then you can separate rail cells, you can separate WBCs, you can separate RBCs, whatever you want is possible through this map that we have developed. We are waiting for filing the patent, getting the numbers, and then make it public. And here I want to show you that the work that we are doing is the work that all other around the world are doing. So these are some commercially available tools for CTC isolation. For example, this is Telbio. If you remember the first slide that I show you from Mehmet Toner group, the group is exactly this channel. So their group in 2021 raised $5 million for this company to separate blood components. We have a nice company which called Cellular Highway, which they have used the vortex phenomena and inertial phenomena for separation of the cells that they want. And we have the Railcell company. The Railcell company is a really advanced company for separation of the components. So these are all commercially available tools for CTC isolation. And at the end, I would like to finalize the workshop that we have here together with these microfluidic channels that we have developed. We call it cell washing or cell washer. So what we have proposed here is that through a magic color that we have shown here, we are able to separate the cell of interest from a mixture of particles and then put them through this outlet. So imagine just what? Imagine you have cells with stains from this outlet and you have fresh buffer from this outlet. So what you will get is that you will get the stained cells from this outlet and you will get all those staining that are in the solution through this outlet. So you can save money here for those who are expert in flow cytometry. You can save a lot here, because you have lots of stains that are here and then you can reuse them. At the same time, you reduce the background noise in the flow cytometry data. which is really, really common in the flow cytometry application. And lots of other applications that is in our mind toward development of this device. We call it cell washing. You are seeing how the desired cell is drifting through the channel. You are seeing they are focusing all in here, and they are all coming through this outlet. And here is a cell-free media outlet. So you are seeing here, you don't have any cell. All here is just stained. And here are all those cells that are coming toward this outlet. All I want to say to you guys is that microfluidics is coming. Microfluidics is coming toward all different fields. Yesterday, we have innovation cytometry workshop that is run by Rob. And here, one of those guys, the bio, it said that the microfluidics is the solution for the future. This is absolutely correct. I can't be agree more. Really, microfluidics is the real solution for the future. And if we understand the phenomena which is there, and if we understand what's happening toward those tiny channels into the microfluidic devices, I promise you, you can develop some cool research ideas, some cool products that was really impossible with doing in a conventional laboratory. So here I would like to especially thank my friend Rob, Professor Majid Bakiani, my supervisor, Helen and Felix for organizing this fantastic workshop and the whole conference. Thanks to ACS Cytometry Society for providing us this opportunity to talk with you guys, to share the ideas and to say what's the state of the art. I hope you like this microfluidics workshop. I would like to thank all my collaborators in Bakiani Lab all around the world. And if you want to have, some collaboration, some connections together, this is my LinkedIn, my Twitter, my research kit. My email address is there. If you Google it, you can find it from the ORCID or everywhere that you want. And I'm happy to help you, happy to collaborate with you guys. And this is the end of the workshop that we have prepared for the microfluidics. So if you have any questions, I'm more than happy to answer. And then that's it. So if you have any question, please let me know. I'm more than happy to answer, especially those applications that we were talking. I would say these needs to have lots of efforts for development of a nice product out of them.
Hi, Sajad. I got one in terms of some of these new devices that specifically target the smaller particles, say for example the 1 micron
Yes.
exosomes, and that. How sensitive are these instruments to changes in pressure? And is this going to be a major hurdle in terms of commercializing some of these systems?
Fantastic question. That's fantastic. So it means that you understand the pressure is really hard here. So that's true. That's true, because the pressure is the major problem of us toward commercialization of microfluidic devices. So you know that PDMS made microfluidic devices is a less viable option for being commercialized, and all are moving toward having the injection molded microfluidic channels rather than those PDMS made ones. So based on this and based the interaction that I have with different industrial people out there, from the beginning, I developed all my channels with hard material rather than soft material, to make sure that I can damp the pressure before coming into the system. And at the same time, because we are waiting actually for getting the IP file number to release the data. But we have developed a method where we can damp the pressure within the channel. So we don't see the problem of those pressures that you are seeing in the normal PDMS made channel in here. The other work that we have done here is that we increase the band of focusing for the channels. For example, if a particular microfluidic channel is working from flow rate of 1.5 to 1.6, we make it to work from flow rate of 1.5 to 10. So if it goes in any band of these, it will show you the same behavior, the same focusing channel, everything would be the same. And this is the same for that exosome separation microfluidic device that you have seen. So we are now able to separate submicron particles, means 200 nanometer, 500 nanometer, 800 nanometer. We are able to separate 1 micron, 3 micron, 5 micron, 7, and then the rest. So I think if I answered you.
Yeah, you definitely did. Thank you.
So, yes.
Yeah, I'll ask another question. As far as cost for production of these systems, because obviously that's sort of still somewhat of a barrier of entry, because if you're getting a specialized microfluidics device, a lot of the times it's going to have sort of applications in your lab, and then you may be going to be pushing it a little bit for institutional funding to get that sort of stuff for finding grant money for it. Is the cost still decreasing? What's the projections for cost on microfluidic devices going forward?
Okay, that's really cool question, I would say. So you know what's happening here for the cost of microfluidic separation devices. What we are going to apply is that, because, for example, let's say for the CAR T-cell therapy process or for the bioprocessing process, we aim to have 1 cartridge for each run. So it means that if you want to have 12 runs per day, you will have 12 cartridges per day. So the major cost of the machine would be the cost of the cartridge. But since we are going to develop these cartridges via some rapid prototyping methods, so the cartridge that you are going to get is much lower in terms of the price, is even from the maintenance of a big machine. You know, because for maintenance of a big machine, even the technicians wants to come here and see the machine, we have to spend a lot. But we were saving a lot by producing massive, and the main money would be the money for buying the machine to run that, and the other would be the cartridges. But something that we are doing very recently means that today after lunch, I see a successful prototype in our lab, which my friend is creates that, is that we are moving towards having some handheld microfluidic devices. So imagine that everything that you are going to do is just a channel, and that's it. You don't even need to have the machine. So even the big cost of the machine here is going to be reduced. But these are for some particular applications. For example, when you have rail cells and you want to separate those rail cells from 1 ml of sample, then these single-use handheld cartridges, microfluidic devices are good. But for other applications, I would say we need to further tweak it.
Fantastic.
Hi, Sajjad. Fantastic talk. Thank you very much. I do have a sort of a question towards how these microfluidics do you think you wait to. So what we've seen today, what we've shown today is the workings, development of the system in themselves, separation, all different methods, vortex or electromagnetic separation, things like that. But at the end of the day, for example, when you work with cells, whether you're cells that have to be gotten to single cell level, passing through this process, at the end of the day, your collection of cells will be in a certain volume. What do you think down the track? You know, we've talked about miniaturization of volumes, you know, bringing down the volumes to work on single cells or smaller volumes of cells, so that you volumes of reagents are going to be lower and lower. But I mean, I'm just looking at the way the cells being collected from these current what do you call it, devices. It looks to be quite a big volume. And trying to concentrate that, you can still have to go through a step of, say, centrifugation, which then could potentially affect cells transcriptomics, or that kind of stuff. Where do you think these will go down the track? With the volume, would there be a way of getting that volume to really tiny and things like that?
That's amazing. So this leads me to show you this slide. Exactly, we have this scope here. So previews here. So I told you this is the map that based on this we are developing channels based on the applications that we want. So what you are talking about is exactly our concern, is that, okay, we are doing the job of separation. For example, we are getting the CTCs, we are getting the CTC clusters out of the cell population. So now, so what? We have 1 ml of cells, and then how we want to separate them again, how we want to make it to 100 microliter, to 10 microliter, to do the single cell analysis and put them on in all those sorts of single cell machines and things like that. What we have developed and what we have worked on that is that after we do the separation in here, we are using some single cell trap devices. Means that we have calculated the hydraulic resistance and match the flow rate of output of our device to the input of the single cell analysis devices. So we have created some tiny single cell capturing pockets, static droplets, we call it there. Then we connect the output of the channel to the input of those single cells. Then we will have one array of single cells that are sorted, and all of them are in the pocket. And since we have a reversible bonding methods for these, you can easily debond your PDMS channel and then collect them and then manipulate them with the micro manipulator or the things that is in your mind. Another application that is absolutely true based on what you said is development of this machine, actually. This machine. So here, the amount of concentration of cells that I put is 1 million per ml. Means that the pack of cell that I get here has 50 million cells per 5 ml. So imagine that you have a sample after post-processing of a device, that the sample volume is not the one that you want. So we have these super concentrating channels that concentrating the cells 10 times, 3 times, 5 times, depends on the applications that you want. And we can do the recirculation. So it means that if you do 10 times, you can recirculate it and make it 10 times more. So at the end, you have 100 times concentrating the samples. So although the concentration of the cells will affect the performance of our device as well, but at the same time, we can get the amount of low volume with high concentration based on what you want and based on what is desired for the application. But the thing that you are saying is that absolutely true. All we are going and all we are doing here is that to just don't do the centrifugation. This is our main goal, actually. And for that, we have developed different sort of components for reaching the aim.
Cool, thanks. That's really exciting.
You will see the article very soon. Then I'm happy. I hope that we can do the collaboration. You can see the technology, you can adopt it, you can make it nicer, make it better. All of these are happening. So if you have any question, please let me know about the devices, about microfluidics, about cytometry, about how we can do the fabrication, how we do the numerical simulation. Just one part, just one hint about the numerical simulation is that really make sure to invest time on that, because at the very end, if you be a really experimentalist, you understand the physics by numerical method. All the developments that I have done so far is that because I understand the physics based on the numerical modeling. Otherwise, if I don't know what's happening there, it's impossible to understand what I'm developing. So So I want to emphasize more that numerical stimulation is really good. It's really enlightening for you to understand the pure physics, the background physics out of that. And at the end, I would say that it will give you a good package for your future. If you want to be entrepreneur, if you want to develop something, if you want to work somewhere, if you want to go in an R&D section, all of these, it would be possible for you based on the packages that you have prepared for yourself. So do you have any question here? Let me check the chat. So thanks for the nice word, guys. I really hope you enjoyed. Really hope you enjoy and you like. It was all to make you guys familiar. That's it. We all want to make sure that you like the microfluidics, and just I want to give you one simple message that microfluidics is coming, guys. Microfluidics is coming.